Hi guys, welcome to another chemical engineering tutorial brought to you by the ChemEng student. In this lesson we're going to take a look at the top technical interview questions and the responses that you need to give in order to secure your next job. So what we're going to cover here is, because any interview, especially for chemical engineers, can be incredibly daunting, and that's why this tutorial aims to cover some of the most common and most difficult technical interview questions, specifically designed to find the perfect chemical engineer for that job. Now we're going to cover the top 15 questions and we'll provide detailed responses and explanations as to what these questions are intended to find out. Now it's important to note that these are only a selected few of the most common and most difficult questions that you can be asked. If you go into an interview, then you could be asked several other different types of questions, so please just bear that in mind. We do have a blog post which goes into another further 20 interview questions, which I'll put a link in the description to that post, and you can check that one out as well. Now, the interview format with most engineering interviews does follow the same general process. Now, typically, you should expect some, or if not all, of the following stages within your interview process. So the first one would be that you submit your CV and your cover letter. And then after that, you would normally be contacted to perform a pre-screening or behavioural test. And this would involve you answering questions such as, how would you deal with, say, an argument in the workplace? Or how would you respond to violence in the workplace? Then these are just behavioural tests to see if your responses fit with the company's values and views. Now this can be followed by either a phone interview or a panel interview. Now within either the phone or the panel interview, you can then be asked a series of technical questions, or you could perhaps be asked some general questions. And say, for example, if on the phone interview you have just general questions, describe a time when you had to do X, Y, and Z, you use the STAR method, then normally what would happen after that is you would be invited to either a panel or a technical interview whereby they will ask you more specific questions related to that role. And another common thing that they like to ask, especially for engineers, is they'll have open day group sessions for group interview activities. So it's just to see how you would interact with your fellow colleagues. Now we're going to look at, as I say, 15 questions. So we'll look at each question and then a detailed response. So feel free to pause the video after each question is shown and see if your answer falls in line with what we recommend. Now these are based on several years of experience as chemical engineering lecturers and studying chemical engineering, so please leave in the comments what you think of our answers, and if you have any other questions that you would like to ask, please feel free. We always like to read our students' comments. So question number 1 is, what is the difference between unit operation and a unit process? Well, the type of answer you should be given here is stating which one is which. So a unit operation is simply a change in the mass or the concentration of a material when the energy from the external source is provided, i.e. we provide energy, say in the form of heat or say electricity, in order to change the mass or the concentration of a given species. Now the key thing here is that no chemical change will actually occur. So an example here would be the boiling of water, because we input the energy of heat and we change the mass of liquid water because we start to vaporize it. Whereas a unit process is the change of reactants, and this is caused by a chemical reaction when energy is provided. Now an example of that would be, say, the baking of a cake, because the change actually happens in the mass and the concentration of the initial reactants. So things like the flour, the eggs, the water, those change due to a chemical reaction within the mixture that causes a new compound to form. So that's the difference between a unit operation and a unit process. Question 2 asks us to explain the concept of thermodynamics. Now, thermodynamics is a core part of chemical engineering. So, thermodynamics is a branch of physics that studies the movement of heat, the pressure, and the volume between different objects. The thermodynamic process is concerned with the interactions among this heat, the work either provided or required, the temperature and the energy, and how these changes can generate and change between one another. So remember, it comes down to the principle that energy cannot be made or destroyed. It can simply change from one type of energy to another. So that's the core concept of thermodynamics. Now, following from that, they might ask you, well, can you define what the third law of thermodynamics is? And granted, they could ask, define the zero law, define the first or the second. But here we're going to define the third law. So the third law of thermodynamics states that whenever a system reaches the absolute zero, the entropy of the system will reach its minimum value. I.e., if we reach absolute zero temperature, then we would assume that the entropy or the state of irregularness becomes almost zero. So we have no vibration. Now, in layman's terms, if you want to also explain it in a more generalized sense, then we can say that a reduced system to a static state where there is no activity, therefore we simply imply that the moving relative to the absolute zero becomes minimal. So, i.e., we have no activity at absolute zero. Question 4 is, what do you understand by the wet bulb globe temperature, and how would you use it? So this here is, you cannot get this confused by defining what the wet bulb temperature actually is, because what this is discussing here is the wet bulb globe temperature. So the wet bulb globe temperature is an international standard that was invented a long time ago when scientists discovered that the dry bulb temperature was simply insufficient, in that some places across the world have more moisture or a higher humidity than others. Therefore, relying on the dry bulb temperature wasn't sufficient enough to account for more humid climates. So therefore we needed something, and we developed the wet bulb globe temperature. And this essentially measures the sultriness of the environment based on the airspeed, the humidity, and the radiant temperature, because all of these factors can significantly affect chemical processes. Because if we have high humidity, even down to very primitive examples, say you try to light a fire in the Amazon rainforest, then a lot of the time it's almost nigh on impossible, because the air is so humid that if it's 100% humidity, then therefore there is so much moisture in the air that creating a fire would be pretty difficult. Whereas in a very dry and low humidity environment, say the Sahara Desert, then creating a fire would be incredibly easy. We could almost have spontaneous combustion. So that's just the idea as to how to understand and how it can actually be used to, relate the real life scenario to the theoretical idea of the wet bulb globe temperature. Question 5 is, what are some of the important safety measures that should be in place in a laboratory environment? Because remember, safety is one of the core aspects of any engineering application. Now, a typical answer that you should try and incorporate is things like saying that you would research and keep up to date with the safety protocols, because all the time protocols change, they get updated, some information may be added, so it's ensuring that you keep up to date. Making sure that your safety gear or your PPE is in full working order, and that it is suitable for the conditions that you're going to be working in. So if you're going to be working in a radiation environment, then you want to ensure that your radiation suit is suitable for the levels of radiation that you're going to be working in. And you should always be prepared in case a safety incident occurs. So that's ensuring that you are current with the company's policies, you are aware of the safety of the chemicals that you're working with, so that's referring to things like the MSDS, and then also ensuring that your colleagues are familiar with the safety procedures. And that would be essential for, say you were bringing on new members of staff, or you were beginning a new project. Then ensuring that everybody is on the same page, and that safety guidelines are followed, then that would ensure that everybody is kept safe. Question 6 is define the octane number. So a very simple question that pretty much all chemical engineers should be able to answer. And an octane number is defined as a resistance to an explosion of a fuel, specifically within a spark engine ignition system, i.e. a diesel engine, or potentially a petrol engine as well. So when we make a comparison between the isooctane and the N-heptane mixture, so what we mean by that is the higher the octane number, the more efficient the fuel will burn. So high performance vehicles tend to have fuel with a higher octane value, i.e. we have a higher ratio between the isooctane and the N-heptane mixtures. Question 7 is, what is a solvent? Because we use the word solvent a lot, especially in chemistry, and it is, when we deal with chemical reactions. So a solvent, in simple terms, is a liquid that can dissolve, remove, or suspend components of a given material without making it undergo any chemical changes. And these are used as, say for example, cleaners. We can use them for carriers, and even separation means for a number of different materials. Now, very common examples of solvents can be things like water, alcohol. We can even have ionic liquids and some amines. So as part of my research, I use tertiary amines, one known as NN-dimethyl cyclohexylamine. And that is a very powerful solvent that basically allows us to switch the polarity between hydrophobic and hydrophilic. So you can get very simple solvents, such as water, and you get very complicated solvents, such as the tertiary switchable hydrophilicity amines. So if you want to learn more about this, then please feel free to contact me via our website. I'll put a link in the description to our website if you want any more information on the solvents. Now, following from the solvents, there are 3 classes of organic solvents. And the question would be, can you tell us about them? So the first thing that we need to ensure is that you know the 3 classes. So the 3 classes of organic solvents are hydrocarbons, oxygenated, and halogenated. Now, oxygenated solvents are things like alcohols, ketones, and esters. Hydrocarbon solvents include aromatics and alphatics. And halogenated solvents are things like chlorinated agents, because it tends to be in the name. Hydrocarbons, aromatics are made from carbon and hydrogen. Oxygenated solvents, they perform oxidation reactions and reduction reactions. So that's things like alcohols, ketones, esters. Granted, these are hydrocarbons, but they perform oxygenation reactions. And the halogens, so the halogen series, which contains chlorine, fluorine, etc., then an example here being chlorinated agents. Now, they're all used for specific purposes, and it depends on the material and the nature of the chemical reaction that you are actually going to use as to which one is going to be the best solvent to use. Question 9 would be, can you define flow control? Because as a chemical engineer, one of the core things is fluid mechanics and fluid dynamics. So how could we control the flow of a given material? So if we define flow control, it's essentially the process of managing the movement of a material through a production or a distribution process. And it optimises the material, the equipment, and the different processes associated with the flow or the movement of material. Now, say for example, we couldn't specify a piece of equipment with a capacity of say 800 units per hour, when the projected volume would only be 400 units per hour. So therefore, the process is managed through the use of sensors and monitoring equipment that are found at critical points within the production process. And the way that we would find these critical points is through optimization. So we could perform several different optimization techniques, and we could actually determine where these critical points are and then work out how we can actually implement these flow control systems. Now, if you want to learn more about process design and safety concepts, then we do have a free and other online courses. I'll put a link in the description to some of the courses, and you can check them out as well. Now, question 10 is, what is a CSTR and what are its basic assumptions? Now, reactor design is something, is one of my specialists, and we do have a fantastic reactor design course which goes into a huge amount of detail on how to design, how to optimize, and how to really design true-to-life reactor systems. But here, CSTR stands for a continuous stirred tank reactor. And these are one of the more commonly used reactors within several industries. Now, the basic assumptions when we model a very simple CSTR would be we assume steady state conditions, i.e. what comes into the system leaves the system. We have isothermal conditions within the reactor itself, i.e. we have a constant temperature, so we don't have a change between the inlet and the outlet. We have a one irreversible first order reaction kinetics. So therefore what we say is that if we have A plus B goes to C, then it's going to be of the first order with respect to species A. And then we would say we have an adiabatic, or a no heat loss to the surroundings, or heat gain from the surroundings. So we assume a perfectly insulated reactor. And that's the basic assumptions that we would need to apply when we design a very basic and simple CSTR. Question 11 is, what is the major difference between extractive and azeotropic distillation? Well, if we define each of them first, then we can define what an azeotropic mixture is, and then we can see the difference. So extractive distillation is a chemical engineering process in which the formation of an azeotrope is needed. There is no formation of an azeotrope which is needed to separate the components of a compound, i.e. they can be extracted in the same vessel. Whereas an azeotropic distillation requires a second azeotrope to break up the components of the initial azeotropic mixture. For example, ethanol and water. So ethanol and water form an azeotropic mixture, i.e. their boiling points are very, very similar, because an azeotropic mixture by definition cannot be completely separated because their boiling points are very close. So even by changing the pressures, because the boiling points are so close, and distillation requires a distinction between the boiling points in order to separate them, then azeotropic distillation requires subsequent units as well, or the addition of components which will allow us to break up the azeotropic mixture. Now, question 12 asks us to explain what Reynolds number actually is. Now, any chemical engineering student, any chemical engineering professional should know Reynolds number inside and out. So Reynolds number is a dimensionless number used to describe the behaviour or the nature of fluid flow, and it comprises of the fluid velocity, the viscosity, the density, and the pipe diameter. So we have a free dimensional analysis course which allows us to go through the process of developing and analysing these critically important dimensionless numbers. So I'll put a link in the description to that as well. I highly recommend that. It's very, very good for getting used to the mathematics and the engineering, how they marry together. But essentially a Reynolds number, now this is where there's some ambiguity. But a Reynolds number less than 2,300 is deemed as laminar flow, and a Reynolds number greater than 2,500 is deemed as turbulent flow, because Reynolds describes the nature of the flow. And these the values between these limits is known as the transition region. And the transition region is a bit ambiguous because there is no fixed range or fixed value that indicates where the transition region lies. So it's often up to interpretation slightly. But generally, anything over 2,700 for a Reynolds value is deemed turbulent. So it's just ensuring that wherever you get your reference value for Reynolds is that you stick with that all the way through the calculations. Now question 13 is, what is an isochoric process? Well, in essence, isochoric process is a thermodynamic process in which the volume of the closed system remains constant. So we have a constant volume. And it describes the behaviour of a gas inside the container that cannot be deformed. So what we can then say is that since the volume remains constant, then the heat transferred into or out of the system does not follow the P delta V work, but the changes within the system's internal energy only. So therefore, the heat transfer will only take place through a change in the internal energy of the system, i.e. its temperature. It won't do it in terms of its enthalpy. So that's just one thing to note and one of the characteristics of an isochoric process. We also have isobaric processes which lead to constant pressure. So rather than fixing the volume, we fix the pressure. And it all works down on the principle of Boyle's law as well. So you could check out Boyle's law for more information on these types of processes. Question 14 is, suppose we're working on a piping system for transferring slurries, and what are some of the considerations that you would have in mind when working on these types of systems? Well, a typical answer that the interviewer would be looking for is things like the capacity, the surface tension, and the piping materials, because when we deal with slurries, then slurries often exhibit non-Newtonian behaviour. So that's us getting into fluid dynamics and fluid mechanics. So surface tension plays a huge role in how these slurries will actually behave under stress conditions. Now we'd also need to have in mind that the piping system must be able to self-drain, given that the slurries are denser than different liquids. So we'd have to ensure that there is safety systems in place that would allow these slurries in order to drain themselves. Now also, in order to prevent blockages, because sometimes we have what's called shear thickening fluids, that when the shear rate becomes high, the fluid will actually become hard. So it's things like cornstarch and water. If you take cornstarch and dissolve it in water, and you subject that liquid to stress, it will actually become solid. So in order to prevent blockages, we have to ensure that the amount of pressure, we have enough pressure in order to blow out the line. So we need to consider how much, or what's the critical pressure that would allow us to clear any possible blockages within the pipeline. And then the final question, which is one of the biggest answers, I thought we'd leave the best one till last, is for a heat exchanger, will the overall heat transfer coefficient increase along with an increase in the log mean temperature difference around the unit? So this is quite a large answer, but one that is full of detail. So please ensure that you can work out exactly what we're talking about and make sure that this corresponds to what ideas you had in mind. But essentially, the overall heat transfer coefficient, so that's U, is generally weakly dependent on the temperature. Because if you look at the equation, so the U equals QA delta T, then as the temperatures of the fluid changes, the degree to which the overall heat transfer coefficient will be affected depends on the sensitivity of the fluid's viscosity to temperature. So this comes back to the Newtonian and non-Newtonian fluids. So say for example, if both the fluids are water, then the overall heat transfer coefficient won't vary that much with temperature, because water is a Newtonian fluid. So its viscosity doesn't change dramatically with temperature, or indeed shear stress. However, say one of the fluids was an oil, then the overall heat transfer coefficient would be much better at higher temperatures. If the oil had, say, a greater Cp value, it had a higher specific gravity value, then the higher temperatures on the oil side would become limiting. Then, what we could realise here, based on that information, is that the overall heat transfer coefficient is dictated by the local heat transfer coefficient, and that from the wall resistance of the heat exchanger. So, rather than looking at it from an overall perspective, we would need to look at the heat transfer on a local basis, i.e. let's look at the resistances between the heat transfer from the outside of the heat exchanger through the wall into the fluid. Let's look at the fluids individually. Let's look at their local heat transfer coefficients. And the local heat transfer coefficients are then going to be dictated by the fluid's physical properties and the velocity of the fluid through the heat exchanger. Because we're talking local, which means specific. So the local heat transfer coefficient for water would be different for the local heat transfer coefficient for, say, the oil. So we look at the difference in the physical properties of the fluids in order to deduce what these local heat transfer coefficients would actually be. So for the given heat exchanger system, fluid flow rates and the characteristics of each fluid, the area of the heat exchanger and the overall heat transfer coefficients would be fixed. And this would be in a theoretical sense. So there is a lot of different parameters associated with this style of question, but what they're looking for here is to see, do you have an idea and an understanding as to what the overall heat transfer coefficient is? Do you understand how it relates to fluid dynamics, the fluid physical properties, and can you relate it to the transfer of heat in terms of the resistances? And if you can answer that style of question to that level of degree, then you should have no problems in passing the interview. So that's the end of this lesson. Thanks for watching. Hopefully this was helpful in answering some of the most common and most difficult technical questions for a chemical engineering interview. If you have an interview coming up, then I wish you the best of luck, and please let us know how you got on with your interview, and let us know your thoughts on the questions and the answers that we provided. And if you have any other recommendations or any future videos you would like to see, please just drop a comment, and we certainly will pick up on that, and we'll try and do our best to accommodate your requests. But thank you for your time, and we hope to see you in another video.